I want to talk about remote sensing of the land surface in particular, and this presents its own special set of challenges, and I'm sure everyone says that about their particular problem. But the land surface makes up 30% of the global surface, but it's the part that we interact with, it's the part that we live on, it's the part that provides our food predominantly and our shelter, and so we have a particular reason for wanting to understand and measure the land surface. One of the key challenges is the heterogeneity. So if we look at this map, which I'll come back to, we can just see straight away how heterogeneous this land surface is. Now, the parts of the ocean and the cryosphere are heterogeneous too, but not at the same range of scales that the land surface is. So that's one of the key challenges that we have in trying to understand the land surface and to monitor change over time. There are other issues that make the remote sensing of the land surface particularly difficult to do in some respects, is that the system changes in response to climate, in response to us, and it changes at spatial and temporal scales ranging from millimetres and centimetres up to kilometres and up to regional and landscape scales. It also changes in time over a huge range of scales. And so this range of spatial and temporal scales that we have to deal with in remote sensing of the land surface is somewhat of a challenge. The measurements we make are by definition remote. And what that means is that we rarely get to measure the things that we actually want to measure directly. So this is particularly true of the land surface. When we want to talk about forests and we want to talk about vegetation, we want to talk about our impact on the land surface, our management of it and agriculture and so on, typically the sorts of things that we want to measure are the amounts of stuff that's there, what type of stuff it is and how it's changing over time. Those are measurements, or those are properties which are very far away from the sorts of things that we can measure from satellites, where we get to sit above the atmosphere and we get to capture and count photons that are typically reflected from solar radiation that arrive at the top of the atmosphere, and we get to record those in some sort of image data. The challenge is turning those photon counts at the top of the atmosphere into something that we can interpret. So I've got an example of a rather sort of direct measurement that we can use here. This is a lovely image of forest change between 2000 and 2012 as mapped by the Landsat series of satellites. So if we look at this in a bit more detail here, and I'd like to zoom in here, we're looking in the South American Amazon here. I can zoom right in. We can see several things here that are particularly important. First of all, the colour scheme here. The red is change that's occurred, forest that's been lost between 2000 and 2012. So the red bits are bits where there used to be forest and the forest has gone. Green is where there is forest cover in general, and the black bits are bits where there's no forest at all, so we're just going to ignore those for the moment. Blue bits are bits where forest has appeared between 2000 and 2012. Now that might sound a bit odd. We all know that there's forest loss going on all over the world, particularly in the tropics. But there is also forest being replanted, partly for agricultural reasons, but also partly for forest restoration programs. The pink regions we have down here are areas where there's been both loss and gain during the period from 2000 to 2012. So what this map illustrates is, first of all, that we can see large swathes of forest loss. This is primarily due to logging, but also due to clearance for agriculture. Remote sensing of the land surface does this sort of thing rather well. What we can see here is we can see a broad measure of change from one period to another period. And this is built up from aggregate Landsat data over the last 15 years or so that have all been brought together and processed into a sort of common format and then overlaid with this kind of mapping system that we're all familiar with using. We can point and click, we can move around, we can zoom in and out, and we can navigate our way across the globe. However, in terms of understanding how more specifically how vegetation is responding to climate change and how it's changing more subtly, we have to use more sophisticated modelling approaches, and we have to use more indirect methods. So if we come back to this problem of the fact that we get to make rather indirect measurements of things that we're interested in, this is particularly true of the biogeochemical cycles that we're interested in understanding in response to global change, anthropogenic change and climate change. One of the things that we can do, for example, is we can measure radiation that's being reflected from the Earth's surface in a range of different wavelengths. So that's something that is a very common property of remote sensing. We don't just measure at one part of the electromagnetic spectrum, we measure at multiple parts. So we can exploit this ability to measure reflected radiation in different parts of the spectrum to measure and understand the properties of vegetation on the surface. So vegetation reflects very strongly in the near-infrared part of the spectrum at wavelengths that are longer than we can see with our eyes. But in the visible part of the spectrum, the bit that our eyes are sensitive to, vegetation absorbs very strongly. And we know this from our lessons at school, where we see that vegetation uses the chlorophyll to drive photosynthesis. And so this contrast between the near-infrared and red part of the spectrum is something that's very particular to vegetation. So if we can measure this contrast and express it somehow, then it tells us something about how much vegetation there is and how much radiation it's absorbing for photosynthesis. So this map is a map produced from a global synthesis of data from the NASA MODIS instrument over the last 14 years. So we're starting off at 2001 and moving through to 2014. And what we see here, coloured in green, is this contrast between near-infrared and red reflectance. And so through the passing of the seasons, as we go through the year, we see the greening up of the northern hemisphere in the northern hemisphere summer, and then of course the browning down, the senescence of the vegetation in the autumn and winter, and the corresponding greening in the southern hemisphere. So this concept of using this contrast between near-infrared and visible reflectance is something that tells us about roughly how much stuff there is on the surface that has chlorophyll in it and that is photosynthesizing.
So there are numerous methods that you can use when you have remotely sensed data from various sources to estimate how much carbon is stored in biomass, in forests. So you can use optical data. You can use the reflectance in the near-infrared, which is correlated with how much biomass is in the system. But the problem is it's just reflectance, so it's just the canopy that you're looking at. So there's a relationship there, but it tends to saturate, or it tends to give you an answer up until a certain level of biomass. You can also use radar at different wavelengths that can penetrate the canopy and give you a scattering signal based on how much biomass is present in the system. The challenge with a lot of these data sets is that we don't have a very long data record for any of them. So we're just starting to get baseline data, but if you want to look at changes over time, we still don't necessarily have that information. For example, LiDAR is a very recent form of satellite data collection where we just have canopy height. So that's very useful information. It correlates well with biomass, and there are equations that you can apply to forest height to then derive how much biomass is in the system. However, LiDAR is generally pretty spotty in terms of its coverage, both spatially and temporally. So each of these has benefits and drawbacks. The radar sensors are able to see through clouds, so that's really important for those tropical regions where you have lots and lots of biomass, but also lots of obscuring cloud cover for most of the year. But you basically can play those sensors off of each other and use them together to start to get a better sense of how much carbon is stored, how much is being emitted from land use change, and how much is being sequestered.